So this is my 10 rules talk where I give 10 suggestions for things to think about when you're putting together data for publication in papers. So this is a paper by John Ioannidis saying why most published research findings are false. So you just have to take his word for it. He's mathematically proven that if you pick up a paper, the conclusions are going to be wrong. And similar conclusions came from Glenn Begley. This is a commentary published in Nature where he found that only 10% of preclinical cancer papers results could be reproduced. So 90% of papers are wrong. So here's a typical figure in a Nature paper, and you can see there's a bar graph, and at the end of the graph there are little T-shaped things, and I'm looking for 2 words to describe these T-shaped things. What are these called, these T-shaped things, starting with E and B? Error bars are the words I'm looking for. And in this case, what are the error bars? Standard deviations, very good. Standard error of the mean, very good. Confidence intervals, very good. It doesn't say in the materials and methods or the figure legends. So in this one edition of Nature, there were 10 items that had figures with error bars, but only 3 of them said what the error bars were. The reviewers didn't notice that the authors had drawn on error bars but didn't say what they were. So they either didn't understand the data or they haven't read the paper carefully. And the same is true for the editors. So it illustrates there's a big problem with the data in publications. So I wrote to Nature and I said that by not ensuring that all papers that have error bars describe what they are, Nature publishes material that cannot be properly assessed by its readers. And they improved their guidelines to authors and reviewers. And so now it's much less common to find papers in Nature that have figures with error bars that don't say what they are. Since then, a number of other journals have improved their guidelines to authors and reviewers. If you pick up a paper, even if you have no idea about statistics or error bars, if you see error bars but it doesn't say what they are, throw the papers in the trash because there's going to be 1 million new papers appearing in PubMed every year. It raises the issue, well, why show error bars at all? What's the point of showing error bars? Now, error bars are used primarily for 2 reasons. One are descriptive error bars, and they allow you to summarize and describe the data. And the other class are known as inferential error bars, and they allow you to help you draw inferences from the data. In clinical research and psychology and epidemiology, where all of the evidence is statistical, if you're going to show error bars, use confidence intervals because that's often what the journal editors tell you to use, and because they're the easiest to interpret. Now, in experimental biology, it's best not to show any error bars at all, but just plot the data. But if there is a good reason for showing error bars, probably the best one's to use a standard error of the mean because that's what's used most commonly. But the main thing is if you use any error bar at all, you've got to say what the error bars are in your figure legend. Which brings up rule number 2 is that n must be stated, not just the n in terms of for statistics, but in any paper or any figure that has any numerical data whatsoever. So whether it's a graph, whether it's a table, and so on, so you must be easy to know how many times the experiment was repeated, how many replicates there were, how many mice there were, how many cells were used. And if it's not easy to find out those numbers, then throw the paper away. P is a measure of statistical significance. But statistically noticeable would be a better term, right? Because we use the word significance, people think it's important, but it's not important, not necessarily important. It's the probability of seeing a difference of this size or bigger when there really is no difference between the populations you've sampled from. It's like the estimated false positive rate, assuming the null hypothesis is true. And if a result is not statistically significant, you can't exclude the possibility that the difference you've observed are just due to chance alone. The only conclusion you can make is that you cannot make any conclusions. Statistical significance shouldn't be confused with effect size or importance, and the p-value itself is calculated from sample data, so when n is low, the value for p might be way off. In fact, you need at least an n of 30 before you can get any sort of accurate estimate of p. If you're not seeing clear-cut answers, then design a better experiment. You should only use statistics as a last resort. Design your experiments to give clear-cut answers. So the rule of thumb is, and this works for standard error of the mean error bars, if the bottom of one standard error of the mean error bar overlaps with or touches the top of the other standard error of the mean error bar, then it can't possibly be significant at the p is less than 0.05 level. If you double the error bars, standard error of the mean error bars there, and double them there, if double the standard error of the mean error bars don't overlap, then it must be statistically significant at p is less than 0.05. And in this case, double them to there and double them to there, very close to each other, and p is 0.049, so this is statistically significant. Only show statistics for independent data and not for replicates, because the replicates will correlate with each other and they're not even, you can't draw conclusions. For this example, we're going to talk about a Poisson distribution. A Poisson distribution is a distribution you get where you have integer numbers, you can't have less than 0, and in theory you can get a large number. So if you're looking at the number of clones per well in a 96 well plate, some wells will get 0 clone forming cells, some will get 5 clone forming cells. In this case, none got more than 5 clone forming cells. On average, there was 1.6 or 1.8 clone forming cells. Now, the cool thing with a Poisson distribution is the expected standard deviation is just the square root of the mean. So you'll just have to take that on faith. Rule number 5, include 0 on graphs. Of course, this doesn't apply to log graphs, but if ever you're showing graphs, it's best to include them down to 0. So here, for example, you think this bar is much bigger than these other 2 bars, but they should have started their graph at 0, and then you'd say, well, look, these are all much the same. So people who don't extend graphs to 0, you shouldn't trust them. They should be in advertising, not in science. Don't paste together images. I had this one to review for science. You can see the discontinuity here. It was rejected. I got the same one to review for genes in development. You can see they've taken out a blank lane. And all the instructions in journals now say, if you have an empty lane and you take it out, join things together, leave a line, a gap in between. But there's more, because if you look at CASP3 here, you can see a little dim CASP3 in the middle in the pre-bleed. Here's CASP3, but now in the pre-bleed it's down here. So they've not only taken out this blank lane and not followed instructions, they've also changed the apparent molecular weight of the band. And this is starting on the slippery slope to research misconduct because it's altering data. Rule number 7, don't just make stuff up. This is one in gene therapy, and if you look, see a little scratch here in the XIAP, and here's a little scratch here in XIP in a different figure, and there's also a little scratch in the CD95L over there. So they're the same and they're a mirror image, but there's more. If you compare that to that, it's really the same thing. They've just pasted a white band over the top, but there's more. Let's take that one and turn it upside down, and you can see that this one is actually the same bands as this one here. So it's recycling, but not in a good way. So you can change the brightness and contrast, but only if it's done uniform. I'll skip through that. Don't hide the background. And again, if you're looking at a figure, don't print it out. Look at it on a computer screen and then use high contrast, expand the image, change the contrast, tilt the screen if it's a laptop. So if you change the background, you can see this is made by pasting together lots of images, and it's, how do you know whether loading was even or not? Show as much of the gel as you can. Some people say, look, I can't show too much white space because, it makes the figures too big. But my advice is show the whole gel, and if the editors say they're too big, say, look, once the reviewers have accepted the paper, then we'll decide how to reduce the size of the images. Rule number 10, declare conflicts of interest. So this is the last example. This is Scott Rubin, who had to go to jail for making up his data. He worked on Vaux, which is a painkiller. Here's Dorothy Hamill, a US skater, saying how good Vaux is just before she had her heart attack. This is Merck. It turned out in Australia, Merck paid for a medical journal that had all gathered together papers that were positive about Vaux and other drugs of Merck, but nowhere in this fake journal did they say that everything was funded by Merck. So no declaration. This drug, this is the paper that supports the use of the drug, said it causes less stomach upset than other anti-inflammatories. So that was published in November 2000. 2 doctors wrote a letter to the New England Medical Journal informing them by looking at the FDA published data that there were more strokes and heart attacks than indicated by the Vaux study, but the New England Medical Journal refused to publish their letter. This just shows in Vaux you get 3 times as many heart attacks and strokes as you do using naproxen. But New England Medical Journal waited 5 years before publishing an editorial expression of concern. Why is that? And it's because New England Medical Journal sold roughly 1 million reprints of their study, mostly to Merck, generating $700,000 US. The FDA commissioner who approved Vaux left the FDA to go and work for Merck. He later pleaded guilty to criminal charges for fraud. Initially, the FDA report on Vaux was suppressed, but eventually it got released in the in the Los Angeles Times. The study found that as many as 140,000 cases of heart disease in the United States and as many as 56,000 deaths, right? Unnecessary excess deaths in the US alone were caused by Vaux in the 5 years it was on the market, right? This is more than the number of soldiers killed by in the Vietnam War. Of course, a lot less than the number of Vietnamese killed by US in the Vietnam War, but 56,000 deaths, right? In terms of serial killers, in terms of damage and terrorism, this case dwarfs any of the other recent ones that you've heard about. It was taken off the market in 2004. Merck paid $4.8 billion to settle US cases, a further $1 billion in legal costs. That's the end of my talk. I've already gone over time. Any quick questions? 2 quick questions.